The first type of friction we're going to talk about is static friction. So there's a few things to know to recognize when we would have static friction, and then how we're actually going to predict what it will be. So the first is that we have static friction when the object is not moving in relation to the surface. So this is really important. We say that the object is at rest, but that's only in respect to whatever surface it's on. So for instance, imagine a pickup truck going down the expressway and there's boxes in the back of it. We would say that static friction is actually at play there potentially, even though we would say the box is also going down the expressway at 70 miles per hour or whatever it is. But since the box is sitting on a surface and not moving with respect to that surface, static friction is what matters. And we'll actually do calculations related to this where, for instance, you have an object in a truck bed and you have to think if the box or the object is not moving with respect to the truck, static friction is what matters. Even if the box is going down the road, you only think about it with respect to the surface. So the next thing is that it opposes the direction in which it would slip. So let's look at this box and what this means, right? In the case where I am pulling, as the picture shows, we would say that static friction is to the left. Because if I'm pulling to the right and the box is not moving, there must be a force to the left canceling it. But now, what if I had a different scenario where I was pushing from the right? Well, now, if I'm pushing from the right, that means that my push force is acting to the left, and now static friction must actually be to the right. So static friction doesn't always act in the same direction. It's just a question of what direction you need to prevent it from slipping. Now, the last aspect of static friction is probably the trickiest, which is that the magnitude can change. What this means is that when we consider this free body diagram, where our pulling force is represented with tension, and we said that our static friction is over here to the left opposing tension, in this case, we are just saying that the magnitude of static friction is equal to the magnitude of tension. Now, what if this pulling force increases, right? What if people start pulling harder? Well, that means that our frictional force must also increase unless the object starts sliding. Once it starts sliding, it's kinetic friction. But so if suddenly this pulling force now decreases, so does static friction. So this is really important. When you use the equation that we'll come to next, that is the equation for the maximum value of static friction. But in general, in situations where your object is not slipping or it is not about to slip, you have to calculate static friction from knowing what your free body diagram is and saying that in this case, the static friction equals the tension force. That is completely different than the calculation, where the calculation is giving you a maximum value. So please be very careful about this. This is one of the most common mistakes I see students make when it comes to friction. Okay, so to try to drive home this point, when we calculate the static friction, we are actually calculating the maximum value. And this calculation is going to be our coefficient of friction. And one thing you'll note, so this is the Greek letter mu. So this letter, which I think of as U with a tail on the front, this is the Greek letter mu, which is actually said more like, that was terrible, but mu, not just mu. And that's going to be our coefficient. Note that there's a little s, which doesn't represent a direction as S has in the past, but is representing static friction. We'll talk about coefficients of friction at the very end of this sequence of videos, and one thing to note is that for a certain surface combination, the static coefficient of friction and the kinetic coefficient of friction might be a little bit different. Now this is our normal force. I like writing it this way. The book will write it just that way as a n vector. That's absolutely fine too. So whichever way, but just remember that this is your normal force. So Magnitude can be less than the maximum. And this should make sense, right? Like when you're on the expressway and there's a sign that says the maximum speed is 55 miles per hour, you're still allowed to drive 50 or 51 or 52. It's just a maximum value. And so same with static friction, that this is the calculation for maximum. So we can actually use Newton's second law and free body diagrams, as I said in the previous slide. So for instance, as tension is increasing, our friction force is also increasing until it reaches the maximum value. So what the maximum value represents is the most static friction you can have. It's not possible to have more. That's like by definition. So what that means is it starts to slip if your frictional force is equal to your maximum frictional force, and then you have kinetic friction appearing. So that's what happens. If it's starting to move, you have kinetic friction. Otherwise, you have static friction and it balances the forces. So please remember to calculate it from Newton's second law, which remember is just that idea that your net force equals your mass times your acceleration. So if you know that it's not accelerating, which is frequently going to be the case along the surface, then you know that your net force along the surface must be zero. So please be careful about that. Static friction is tricky since the calculation of maximum is different from how we often actually calculate it.